Okay, thank you. So my name is Wojciech Tyczyński. I work in Google for the last 4.5 years on Kubernetes. My main areas of interest are scalability and performance, and that's where most of my focus in Kubernetes is. And this is also what this talk is about. I'm, oops, it's me, huh? So I'm one of the SIG leads, or SIG is like special interest group in open source Kubernetes community, one of the two leads for scalability interest group. I'm also leading this effort internally in Google. And yes, I'm going to talk a little bit about this topic. But before we start, so how many of you didn't play or didn't use Kubernetes at all? Okay, so quite a few. So let's do some introduction so that we can at least to some extent understand like this a little bit better. So sorry, something. Oops. Okay, so, sorry. So as you probably heard, like Google is using containers for over 10 years. I think it's more like 15 years now. The Borg, which is the system we are using internally to manage container, was created in 2003 or 2004, if I remember correctly. And we are starting like 4 billion containers per week, roughly, which means that we started something like 800,000 containers since I started this presentation, which like makes it something that we really wanted to share with the world. And based on those experience, we basically created Kubernetes project. So what is Kubernetes? So Kubernetes is an open source system that is used for managing, scaling, and deploying your containerized applications. So it's been in the market for roughly 5 years now. It's roughly 4 years since it's like 1.0 version in June 2015. And since this word, since then it became a de facto standard for managing your containerized applications. But in order to talk about scalability, like let's look a little bit into very high-level architecture of how Kubernetes works. So at the very high level, like what you should, as a user, what you should really care about is like that there's like a set of machines, a cluster of machines where your containers are running that is hidden behind the API that you as a user are interacting via which you as a user are interacting with this cluster. What is important is that like all the components in Kubernetes cluster are also using only this API. So there are no backdoors. Like everything that our internal components can do, you as a user also can do just using the public API. So going a little bit in more details, so how it looks, how the Kubernetes system looks like. So we have basically two main groups of components that control plane, Kubernetes control plane consists of. What we call like master components and what we call node components. Master components are the ones that there's like some small number of those in the system. Node components are those that are running on every single node, every single machine in the cluster. So as for master components, like the main ones are like API server, which is like the entry point for the cluster. This is like the component that is exposing the API to the users and to other components. It basically doesn't implement any like real business logic. It's mostly about like writing data to our storage, which is like etcd. This is our key value storage where we store the cluster state. It's doing something like authentication, authorization, and stuff like that. So etcd I already mentioned. Scheduler, as you can imagine, is responsible for assigning your containers to particular nodes where they should be running. And there is a set of controllers that are basically implementing the business logic of different like features of Kubernetes or flows or stuff like that. And as for node components, like the main one is probably kubelet, which is like the node this is the agent that is running on every single node and is responsible for things like starting your container, stopping, health checking, restarting if needed, and stuff like that. Yeah, so I think that we are, with this very, very high level like overview, we are ready to start talking about scalability. So what does really scalability mean? So what do we really do if we are saying that we are working on scalability? So in my opinion, there are like 4 main areas that anyone that is working on scalability on any particular, on any system like that should be doing. And those are like, first of all, is like defining what scalability of that particular system really means. It's not that there is like a single definition of scalability that works for every single system in the world. The second is like driving improvements, or in general improving the system to meet like users' expectations. The third thing is like testing infrastructure, and the fourth thing is like tests in general and like guarding against regressions in scalability and performance and stuff like that. And in the rest of the presentation, I'm going to dig deeper into those like 4 topics. So let's start with the first one, scalability definition. So what does really scalability mean in case of Kubernetes? So what users really want is like they want to ensure that like the system they are using is scalable. It's that no matter like how big their particular their application will scale to whatever scale it will scale, the underlying infrastructure will be able to handle that. But what does it really mean? So in fact, if we ask users what do they mean like that underlying infrastructure scale, they don't really know it. And this is even more, like they don't even want to know it in majority of cases. They just want the cluster, or in this particular case, the Kubernetes cluster to work. So what do we do? So we basically define a set of SLIs. SLI is like service level indicator. You can think about it as some metric that we gather like based on like what is happening in the cluster. And set of SLOs on top of those SLIs. SLO is like service level objective. And you can think about it as that metric plus some threshold for which we say it's like it works. And we are saying that like your cluster works if those SLOs that we defined are satisfied. So what we did in like 2015, we introduced those 2 SLOs. The first one is like 99% of API calls return in less than 1 second. The second is like 99% of pods and then containers start within 5 seconds, assuming that images are pre-pulled. But as you may expect, like that's by far not enough. And there are like 2 aspects of not enough here. So the first one is probably something that you can easily imagine, is that like the coverage of this Kubernetes system by those 2 SLIs is like pretty low. Like there are a lot of features in Kubernetes. In particular, you can imagine that networking in your cluster is completely broken. Your containers cannot talk to each other. They cannot talk to the internet. But those SLOs can't be satisfied. So obviously, if the problem that the networking doesn't work is because of scale, it doesn't mean that Kubernetes scales. So that is the first problem with those SLOs. The second one is less obvious, but it's equally important. And the problem is that they are by far imprecise. So for example, like 99% of all API calls, or do we somehow group them? Over what period of time we are measuring and stuff like that. So in this case, like I bet that if I take any one of you and I ask you for the interpretation, it will be different than my interpretation. So that shows that like those aren't good SLOs. So what we are currently working at is, and what's one of my projects that I'm personally involved in, is like trying to redefine the SLOs. And what we are doing is we are trying to ensure that like all the SLOs and SLIs that we have are very precise and well-defined. That they are consistent with each other, which is also pretty obvious why we don't know. The third thing is that they are user-oriented. This is something that I didn't mention, but it's super important that the SLOs are measuring the aspects of the system that users really care about it. The worst thing that you can imagine is having an SLO that you need to maintain, you need to ensure that it doesn't regress and stuff like that, and no one really taking care of, no one really caring about. No user really caring about that. And the last thing here is that we obviously want to ensure like that the other aspects of Kubernetes are really covered by those SLOs. So in the last quarters, we did a lot of progress here. We have something like 10 SLOs now. They are covering a bunch of networking and storage stuff. There's still a long way to go, but we are doing a lot of progress here. So just as an example, like this is how actually half of the SLI and SLO of this API responsiveness looks like. I'm not going to like, it's not the purpose of this showing me this so that you understand it, but it shows that like, how complicated that is. And actually, I'm leaning towards saying now that based on like what is happening in Kubernetes and based on our discussions with like users, it's still not exactly what the users care about it, and I'm pretty sure we will be redefining it a little bit more in the near future too. So it will be even like more complicated. Okay, so that was about like defining scalability, but how about since we have this definition, like what can we do to improve the scalability of the system to what users really want? And as you can expect, like it's not the case that Kubernetes scaled since the very beginning. Like actually, when we started, or when I started looking into that, like 4 years ago, almost exactly, we weren't able to start the cluster with more than 25 nodes. And over the next like 2.5 years or 2 years roughly, we managed to incrementally scale it to support like 5,000 nodes, which we achieved like in 2017-ish. Yeah. So we support like 5,000 nodes in a single Kubernetes cluster, but that's not even half of the story for that. So the problem is that scalability of Kubernetes is actually a huge subspace of different configurations. So there are a bunch of different dimensions in which we can think about scalability. So things like how many containers you are running in this cluster, how big the churn on those is, like how many of those you start or stop like per second or average, how many ingresses do you have in your cluster, and like dozens of others. And all of those actually matter for scalability and matter for how your cluster behaves. So what we did is like we introduced this concept of like scalability envelope, what we call, is that, and what we are saying is that like if you are within this envelope in all the dimensions, then we promise you that the SLOs that we defined previously will be satisfied. And your cluster will not be like terribly broken or something like that. But the problem here is that this envelope is really complicated, and it's like really hard to explain users how it looks like. And like the reasons for that is that, or actually there are many reasons, but the first one is like the dimensions of that aren't really like independent. So for example, like we support like 5,000 nodes in a single cluster. We support up to 110 pods running on a single node, but we don't support both at the same time. Like your cluster will most probably like blow up if you try to do both at the same time. It's even more like the dimensions aren't even like linearly dependent in many cases. So the example of that is number of services in the cluster and number of like backends per service. And the problem here, why the nature of this limitation is like this is quadratic, is that because there is yet another dimension, which is like total number of all endpoints of all services in the cluster that is also like some kind of like dimension in the scalability subspace. And you may think that like since those are like so tightly coupled, like that it's probably possible to normalize it somehow and remove one of those. And the problem is that it's not, because all of those are protecting a completely different aspect of the system, like scalability of AP tables or scalability or behavior of etcd and stuff like that. So we really need all of those to be satisfied in order to make your cluster really work. The first thing is actually a good news, which is that the dimensions, you can try to pull some dimensions and go beyond some of the limits, because like many of those aren't hard limits. But at the same time, you need to ensure that you reduce your usage in the other dimensions. And the fourth thing is that this envelope is somewhat bounded. There are like many reasons for that. I think it's quite obvious that it will be. The easiest explanation for that is that many of the dimensions are directly corresponding to number of some type of objects in Kubernetes. And because we need to store all of them in the etcd, which has a limit on total size of it, like this is responsible for that bounding here. So as you can see, like it's pretty hard to answer the question whether your particular workload, if run on Kubernetes, will work. I mean, will the Kubernetes cluster satisfy the SLOs or not? And it's actually really needed to understand it and really understand why it will work or why it not work to actually do some real improvements. And this is probably the core of the scalability work, is improving the scalability, because it's what our users really want. And we did a lot of those in the last couple of years. So those were like changes, like architectural changes. One example here is probably like introducing or adding a support for protocol buffer as an input format in the API, in addition to like JSON or YAML. We did a bunch of like local algorithmic or code improvements. And we did also a bunch of other things. Like one interesting category here is reworking the limitations of different dependencies. In particular, one interesting one is like reworking the limitations of Go language in which Kubernetes is written. So those who used Go know that it doesn't have any concept of generics or templates or anything like that. So things like, so there is no way to, for example, do a deep copy of an object. If you want to do it in a generic way, you need to use a reflection. And obviously, reflection is like really, really slow. And that wasn't like acceptable in the case of Kubernetes. So what we did is that we implemented our own code generators that are, and we are auto-generating like deep copy methods for different objects in order to like speed them up. And it speeded them up by like 15x or 20x or something like that, if I remember correctly. So yeah, so those are like those kinds of things that we are also doing. But I'm going to describe in a little bit more details two things that are very recent or that we are actually still working on as an examples of interesting problems. So the first problem is what users really care about is that like Kubernetes can very quickly discover the problems of either your applications or underlying machine and schedule or like reschedule your application to somewhere different. And in order to achieve that, we need like a very frequent signals from the nodes so that they can let the control plane know that it's something wrong with them or stop responding if something is really wrong. But the problem is that the current implementation of that, which is like updating node status objects, is very expensive. So what we were looking for is pretty obvious. We wanted to make those node heartbeats, what we call them, like much cheaper. But on the other hand, we didn't want to introduce some specific, like very specific API just for that problem, because as I mentioned at the beginning, like we want the API that all our components are using is the same API that users can use. Actually, it's all public API. So we don't want to introduce something like millions of knobs because like the API will become completely non-understandable. So we came up with the idea of introducing the Lease API. So the concept of lease is like pretty popular in many areas. Like you can implement leader election based on lease. You can implement TTL storage based on lease and stuff like that. So we thought that it's something that is generic enough that users really can use in many other situations. So what we did is that instead of sending like the whole node status object every 10 seconds, we are just sending like this very small lease object and only sending node status when something really changes. Well, there are some caveats to it, but like it's not super important here. So and those lease objects corresponding like being sent by kubelets are also a signal for healthiness of node. So what we get from that? The main reason for why we started looking into that problem is that we were getting very close to the limits of etcd for the total size of state in etcd. And we achieved like between 2 and 4x, depending on the data, reduce in that aspect. But we also like achieved many other gains here. So for example, because the objects that we are sending here are much smaller, the API server has much less work to do because like smaller objects means like faster serialization, deserialization, and stuff like that. So it's much smaller load on API server, but it's also much smaller, which might be surprising for some people. Like it's also much smaller load or many other components. For example, like scheduler. So scheduler. Oh, we have this concept of watch in Kubernetes. So watch is like long-running HTTP request when a caller says that I'm interested in this group of objects, and whenever something changes, like some new object is created or some objects modified or deleted, we are getting that notification over that watch stream. So, and this is like very core concept in Kubernetes, and many components are using watch to be informed what the current state of the cluster is. In particular, like scheduler is looking into like all node objects to know how much space there is on this node, are those nodes really schedulable at this point on time and stuff like that. So less updates on nodes means less work to process those updates on scheduler side. So it really improved a bunch of other components that had to process updates of nodes. And as a result, it also like all of those, it also resulted in improving the values of like API responsiveness, which is like our SLO. So it's like pretty important for us. Okay, so that was one of the things that we are currently working on. It's like actually in beta in the last Kubernetes release, and it became default with that. The second one that we are currently working on is the following. So the problem is that it's really impossible now to have a service, Kubernetes service with more than roughly 5,000 endpoints now, or backends, or however we call them. This is like a hard limitation. And the second one is that if you really create such service, such a big service, then whenever like one of the backends changes or changes its state or something like that, like it really freezes the API server for a couple seconds even in very large clusters. And the reason for that is that we have this API, Endpoints API, what we call Endpoints API, which was designed in very early days of Kubernetes. And basically a single endpoints object contains list of all backends of a given service in a single object. So if the service is large, this object is basically large. So the limitation at CD side for the size of the single object is responsible. It translates to basically the limitation on number of endpoints in a single service. The second thing is like connected to the fact that we have a component called kubeproxy, which is responsible for programming, network programming, and is running on every single node and is programming like IP tables or IPVS or something like that on that node. And that is basically watching every single endpoint, every single update of any endpoint in the cluster. So in large cluster, like 5,000 node cluster, it means that whenever some small backend of one of the services changes, we need to send the whole endpoint object to all like 5,000 kube proxies, which is like, it can be really gigabytes or tens of gigabytes of data. So that's like a lot of work. So what we do, what we are doing actually. So it's pretty obvious that we need to redesign the API here. And this is exactly what is happening here. So what we are doing is we are basically trying to shard those endpoints, shard a single endpoint into multiple ones. And it's nothing very innovative here. But the question is like why we do this? Why, for example, we don't create a singular endpoint object, one for every single backend? Because obviously then change of a single backend will mean that we just need to update this one very small object. And the problem is like, for example, what if I create a service when all its backends already exist? Let's say 10,000 of those. Then we would have to write like 10,000 objects, and that's also like super expensive. So we are basically introducing this concept of shard, and that, even though in like the initial implementation it will probably be somewhat constant or in some precise like interval of values, like it opens a door for much smarter implementations in the future, where controller that is actually creating, writing those objects based on like status of the backends can actually decide like how many of those should be packed into that object and how many of those into the other one. So that is like the API that opens a door for many improvements in the future also, even though they won't be the part of the initial implementation. And at the same time, we are also trying to improve the performance of Watch, which is like super crucial, as I mentioned before. So one of the things that we are looking into is that currently every single watch is treated independently. So whenever we need to send an object to a number of watchers, like we are serializing it independently for every single one, and like, yeah. So basically, this is one just one of the like 5 or more things that we are currently looking at and trying to fix. So yeah, those are like the examples of things that we are currently looking at. There are like much more of them, but I don't have time to like talk about all of them. So yeah, so let's look into the third aspect of like scalability. So testing infrastructure. So anyone who was working on scalability in any project knows that like this is like both hard and very, very expensive. So what we did is like we created 2 frameworks that are Kubernetes native. The first one is like what we call KubeMark, which is a framework that allows us to create a simulated cluster where we are faking some parts of the cluster. For example, we are faking Docker so that the real applications are not running. We have just this fake Docker that is saying, yes, I started this container, yes, I stopped it, or something like that, but not doing any real work. So from control plane perspective, it looks exactly as it would be real cluster, but we are able to run very large cluster, like 5,000 nodes, with much, much, much smaller compute power footprint. And the second tool that we created, or framework, is like what we call cluster loader, which is a framework for very easy writing of like scalability tests. So basically what we do is now you as a creator of scalability test, you just write some YAML or JSON config. And out of the box, you get all the things like measuring all the SLOs during all the tests and stuff like that. So it really simplified writing scalability tests. And the fourth thing here is tests and guarding against regressions. And I think that's pretty obvious. What does it mean? So I just wanted to point into like 3 things. Is that scalability work is, even though we are like working on scalability of Kubernetes, it's not only about Kubernetes. It's also about working with users, because we really want that our tests and also like SLIs and SLOs really reflect what our users need, so that we are working on the right things. It's talking to infrastructure providers. As an example, like our requirements to scale Kubernetes on running on Google Cloud pushed many different dimensions of Google Cloud Platform itself to higher levels, and that is available for anyone using Google Cloud Platform, not only for GKE users. GKE is like Google Kubernetes Engine, which is like our hosted version of Kubernetes in Google. And it's also talking to like dependency providers. So for example, to Go language folks. So probably you didn't hear, but like via Kubernetes, we discovered at least 3 significant performance regressions in Go in really released version of Go. Just when we upgraded Kubernetes to use higher versions of Go, we observed regressions. And we worked very close with those folks to fix them. All of them are fixed, actually. But yeah, so it's really talking to many different people around, which makes this effort like super interesting and super impactful also. So even though you are working on Kubernetes, you have impact in much wider ecosystem of things. Yeah, so that's mostly what I had for today. We are here today also. I'm here to if you have any questions, I'm happy to talk to you. We have a booth, Google booth on the floor beneath us. Yes, and we are like recommending either contributing to Kubernetes. Kubernetes is open source, so anyone can contribute, or we are also hiring in Google. So for Kubernetes in particular. So if you are interested, like I'm happy to talk, or there's my manager at the back here. So yeah. OK, thank you. So that's all I had. So do you have any questions?